So I'm gonna add just a little bit what my background is. It's automatic differentiation, actually. That's what I did my thesis in. And I've been working with Julia since 2016 when the exascale computing project started. We were one of the only projects that relied on Julia as a modeling language. It was a project ALCF, a project about power grids. And yeah, so our goal then was to run on all the ECP machines, and we succeeded in some shape or form. And so today, now I'm actually working on deploying Julia on the ALCF machines for ALCF, and we will see how to do that best and how to support Julia on future systems, maybe. So I assume that there are two reasons why you are in this talk today. One is you are not using Julia yet. You just want to see what the status is. Is it a viable language for programming, for writing simulations? And second, maybe you are using Julia and you're ready to go and you just don't know what the best practice is on how to use it. So I will start with the first group and go progressively. I will really introduce again, because Julia is such a new language. I mean, Python is 35 years old now, Julia now 10, but that's still relatively new. So I will still go through the steps of discussing why one would use Julia, what the advantages are for portability, and then only at the very end, I will go into the specifics for ALCF, how to actually use it on the systems currently and what our plans are. Next slide. Yeah, why Julia? So the history of computer languages. It starts with Fortran, probably, which stands for formula transformation. So that was, or translation, I don't know. That was really for mathematical algorithms, for people back then to write numerical codes. Then in 1969, we had the language C, which was for developing operating systems and systems in general in a portable way. And then 1980, add more structure to the code, make the codes more manageable, more compartmentalized. So that was C++. And then finally, we had Python, which was really that you program as you go, so you can interactively program and inspect your code, change it. There is no compilation step. And the question is now whether one can combine all of these into one. So be able to write mathematical algorithms, be fast, and also have the ease of use that you can interactively program and inspect your code. And on top of it, organize also large codes in a nice way and combine them. So this composability is also very important in Julia. So this is in effect the holy grail and why people in Julia started out. So it's another try at that. It was started at MIT by a couple of people under Professor Alan Edelman, released in 2012 and designed for numerical and scientific computing. Now, one software package that will come up again and again and is deeply interlinked with Julia is the LLVM compiler suite. LLVM it started, I think, well, it started before Apple, but then Apple picked it up. It started as really also a compiler where design came first. So you have really front end and back end nicely separated. And you have this intermediate representation, which is the language in the middle that is a global language that everybody understands, a universal language. So you pass all input languages to that language, and then you go towards the hardware, which are the various backends that you want to run on. It supports a wide variety of hardwares. And even today, most GPU architectures actually rely on some shape or form on LLVM or derivative or proprietary version of that. And so this Julia comes in there, so it essentially picks that up and then uses the LLVM compiler to do just-in-time compilation. And just-in-time compilation has not been in the initial design of LLVM, so that has been essentially added on. And Julia is also the only language of all the front ends that actually makes really use of that, in the sense of that it is a core mechanic of the language. You really, the code is, when you start Julia, there is no compiled code. You compile it as you go. Metaprogramming and reflections are also important in Julia. So metaprogramming is when you write a code that changes other code that you may not even have written yourself. So you can transform code, which we will demonstrate here, has actually great applications in scientific computing. And then it has this, they claim performance of C with a language like MATLAB, which in some way is true. So it should be easy to use. And you have everything, all the tools that so you have package management and also testing, version management, and all of that is integrated into the language itself. So you don't have to, like in C, you have CMake, you have other build tools that you have to use. Julia has everything integrated. And we will see also that this goes even further than that. It really goes also to the binaries that are actually used in Julia.
Michel, we have one quick question.
Yeah.
Alfred is asking if Julia is object-oriented or not.
It tends to be not. I mean, it's more inspired by functional programming. So you have functions and methods, and for objects or structures, you define your methods. You could write, in theory, you could write object-oriented code in Julia, but that is not encouraged nor done really.
He is asking, so how is the lack of object-oriented can be good for large codes?
We can maybe get to that. I mean, you use functional programming as that to compartmentalize the code and have, and I will demonstrate it later. I mean, it will come and then we can maybe pick up that discussion again. It's a different way of coding.
Sounds good. Thank you.
And one observation also during ECP, and one reason why we picked Julia, is that you may have seen that a lot of the research codes, the effort that goes into the actual research goes more and more towards the software, maintaining codes, and maintaining codes, adding features gets more and more costly. You have to support multiple hardwares, etc. And Julia is also there to make that easier for the scientist, so that you can write more compact code, focus on the algorithms, and you actually leverage also what I just mentioned, the functional programming paradigm to use other codes as templates to essentially do the transformations that you want. Here we have an example of IPOpt. That's the standard solver for nonlinear programming. So if you want to find the minimum of a nonlinear function, it's a 20-year-old code, I think, roughly, and it's really battle-hardened and the reference code. So that's 100,000 lines of code, and then there's MAD NLP, which is also used in our group, and that has only 6,000 lines of code and also supports GPUs, which IPOpt does not. So that gives you an idea about how compact code can be written in Julia. This also has downsides. We will see that also later, but it really leads to very small code bases. So again, just to get back to to LLVM, which is the compiler that is used, and so you have Julia, and it passes your code, and that's the front end, and that then goes to the back end. But moreover, in Julia, you can also manipulate your LLVM intermediate representation and change it at runtime, which is very, very powerful. The disadvantage is that LLVM wasn't created with it in mind, meaning that Julia had from the very beginning this startup time issue and this effect that when you run your code for the first time, you will have to wait for a long time because it is actually compiled and compiled with a serious compiler. So it's not an interpreted language in that way. So the classical setup in HPC and the foundations of HPC have been for the longest time, I think, BLAS, LAPACK, LINPACK as the linear algebra cores of most numerical codes. And then you have MPI for doing distributed computation. And then on top of that, we then had the development of MATLAB, which gave you a nice interface to play with BLAS, LAPACK, LINPACK, and all these libraries, and has, of course, evolved much further now. And then there were the libraries, PETSI and other libraries that were developed on top of this foundation to then write applications that are portable and also applications that are written in a more compact way that is more readable for the domain specialist. So we have an abstraction for high performance. We just call a library with a certain interface for certain linear algebra operations and then expect that those will be executed on each hardware fast because you use the vendor libraries. And the same for API for MPI for distributed computing and using your network efficiently. So what is new is that now in terms of programming, at least from my point of view, is that there's a new paradigm how you program, and that is what used to be just simple functions that you would use, like a stencil or so on, now become these kernels that also have to be portable. Every vendor has a different domain-specific language for it, and that's why then portability layers were introduced, like COCOS and so on, where you can write the kernel in one DSL and then have it run on various machines. Now, first of all, I want to mention that Julia and HPC legacy software, or legacy, yeah, I shouldn't have called it even legacy software. So, I mean, just the software that is being used right now, there's a huge benefit in it. Like, those are codes that have been tested and validated for a very long time. Nobody will throw that away. You will, I mean, you will use those libraries. And what Julia also wanted to make very easy is that you can call C libraries in a very easy way. So as long as your library has a C interface, there is no problem to call it from Julia. You just look for the library, and you get a pointer to the library. You here, for instance, you load the function puts, and then you define an interface where you use the Julia internal method ccall, and then you can call your C function. And you can do that with very complicated objects, and yeah, that's very nice, very easy. Now, the same is also true for Python, although for Python, one would argue that you would call Julia from Python. However, that is due to the fact that Julia is the new language. It was more important for the Julia folks to be compatible with to call Python than the other way around. And the next step is, so we have a package manager, so you install software packages, the versions gets resolved automatically, you have a testing environment. But then the binaries that are being used, Julia also provides a building system for binaries, which are then artifacts. So there's a cross-compilation system where you set up your build script, and it will be built for every libc that is available. That is Windows, Mac OS, Linux, and you can then incorporate that into your code base and call those libraries at very specific versions. So what is also very important in Julia is reproducibility. So you have this manifest file at the end after you run your code and have resolved all the package versions. And if you want to reproduce those results, you just do instantiate. So you save that manifest file, you do instantiate on another system, and you get exactly those binaries that you used. So, and here is the example for one API. So one API is what is used on Aurora, right, for programming on the GPUs. And I actually managed to use all the cross-compilation, to use that cross-compilation system to compile the Intel libraries on that system. So I'm here at home with an Intel GPU, a consumer-grade GPU, a 750. And I just do add one API. So I add the package one API that downloads everything, also the binaries to run, so the Intel binaries. And you will just have to have installed the Intel driver, which is integrated into newer Linux kernels. So if you are on Linux kernel 6.17, you have the Intel driver, you do add one API, it downloads all the binaries, and you're ready to go to write GPU code. And then you can later take that code, take it to Aurora, and the same code that you ran on your laptop will also run on the large system then. So portability in Julia. Why is portability so great in Julia? And that comes down again to this meta-programming feature that it has, so it can transform its own code. You can write code that transforms code. It starts with that all the vendors use some form of LLVM IR or SPI-V. So you have CUDA, ROCm, and the Intel Compute Runtime. And then also for the host, for the CPU, you have just regular LLVM, so which is essentially the standard pipeline for Julia. And then Julia has packages called GPU arrays.jl and kernel abstractions.jl. They transform the LLVM IR that comes out of Julia and transform it for the various backends using those binaries for those backends. Kernel abstractions defines a kernel language, and GPU arrays, you can do operations on arrays that then get translated into GPU codes. We will see examples now. And BLAST and LAPACK is also taken care of. So if you call multiplication, matrix times vector, it will automatically dispatch to the right BLAST of the various vendor backends based on the array type. So the distinction which backend is to be used is based on the type of the array. So in Julia, you have the standard array. So then you have your Q array, you have your ROC array, and you have your one API array. And then you can also abstract your code, of course, away of the array type and just set that at the beginning when you run your code, and it's a portable code. Now, it's using the vendor toolchain, so the compilers are really highly optimized, and you get really performant code out of it. But there are simplifications and choices that were made in Julia. Julia still focuses on user friendliness. So at some point, they decided that for GPUs, the kernel execution is ordered. So you launch them in a certain order, they will be executed in that order, and synchronous. So if you really want to have high performance and you want to do all that fancy that you launch 1,000 kernels and you do the graph optimization, how to run them most efficiently, then you would not use Julia, at the moment at least. And you would write that highly optimized library still in C and C++. So here is the first type of how you can write portable code, so portable kernels. And this is done using kernel abstractions. So you use the package that you want to, that implements your GPU implementations. So one API, CUDA or AMD GPU. Then you use kernel abstractions, which is that translation layer that translates your kernel into the backend kernel. Adapt is another package that is used here. So every backend has a backend object. So one API backend, for instance, is the one API backend. You create that, you pass it, you create an array of 10 ones. That's what ones 10 does. And then you adapt it to that backend, meaning it will be moved to that backend. So it will then live on that GPU. How we switch devices and so on, I keep that away now, but yeah, basically you always have one active device. So this all assumes that you only have one device for now. And then we have the kernel. So this at, that is a macro, and that hints at that macros are what is being used in Julia to transform code. So this code that follows this macro will be read in essentially and then transformed. So this is not actually the real code that is run, but it's being transformed later on. Then we have the index, which is the same than in CUDA or AMD GPU, like a work item, right? You get the index and we do here a my sum, so a pointwise summation. And yeah, this executes that. And here you instantiate the kernel. So we call the kernel, and you see already that the arguments changed here. This is not called with C, A, and B, but you call the kernel with the backend. This then compiles the kernel for that backend. And then you can call that, then you get the kernel returned, and you can call the kernel with CAB and the number of work items. And this will give you pretty fast code for a given kernel, because this uses really the vendor backend. Yeah, that's very neat. And then the other abstraction for ease of use, so this focuses more on ease of use. A lot of the code that you write in HPC is actually not performance relevant, right? So you have mostly one hotspot where you really go deeply into optimizing, and this is more for ease of use, such that you can just write the code where you set everything up that is easy to write. And that uses GPU arrays. You don't have to load that package specifically, but you have again the backend. You again have the arrays, you load it on the GPUs, and then you have this broadcast operator. Those of you who used MATLAB, they probably know this operator, so you can do pointwise operations. This operator can be applied to any function. So you could here, for instance, call sort dot, and it would be applied essentially to each element of C, which in this case doesn't make much sense, except if C would be a list of lists to be sorted. And this provides then also at the same time so Julia has a lot of built-in functions like sorting, multiplication, and much more that you would also have in MATLAB. And it provides a lot of these functions where a GPU implementation is reasonable. So for instance, this calls, if you're on CUDA, this will call actually the sort of that CUDA provides. Or on one API, it may also fall back to a Julia implementation of a kernel if the vendor doesn't provide that implementation. Yeah, and here same for matrix vector multiplication. So I compute Y, So exclamation mark always means in place method. So it only operates in place. It doesn't allocate new memory. That's why I have to give it the y as an input, which is similar than x. So this is how I pre-allocate before I call mul in this case, and then compute a times x, and it will also return what has been allocated here. And this will dispatch automatically to the BLAS. And as you can imagine, most methods that provide a GPU implementation are of these in-place type of methods that only change the arguments and change the arguments in place. And here we see MPI then as the other big ingredient that we need to do HPC. There's an MPI package which maps down to the MPI libraries. It has a way of easily switching the library in the backend. So you can have on a system multiple MPI libraries, OpenMPI, MPitch, and then you set it up. You tell it, I have not now that example code, but you tell it use MPitch, this library, it will use that library. Use OpenMPI now, it will use OpenMPI. And this is how MPI then looks in Julia. You see that this makes also life easier than there because you can leverage what Julia can do, for instance, for derived types. I can define a type here, the derived type, which has some abstract vector in it, which could be a GPU vector or a CPU vector. I mean, it could be one API vector, a ROCm vector, a CUDA vector. And then again, I do like with the backend, I just move that array. So I construct the derived type, and the vector type will be of type of the backend that I have selected. And then I can send that and receive it. So this does a round robin, yeah. And yeah, and this works. And on Aurora as well and Polaris, to just jump ahead here, they both support GPU-aware MPI. So you can pass in here a CUDA array or one API array, and it will just be sent using whatever implementation is used on that machine. And it will not be copied back to host. And now we come to how you program in Julia and what is the advantage over object-oriented programming, or not the advantage, but what is also different. So you use methods and functions as the main way of abstraction. So what is not in the focus, so in object or orientation, the object is at the focus. What can the object, what is the object? And the object has the functions in it. Now, in Julia, it is what functions do you have? And you can pass it any object. And then at runtime, it will decide what it will be dispatched to, whether it can derive an implementation, whether there's a specialized implementation. So that would all be done via type hierarchy. An example that I want to use here is, for instance, Krylov.jl, which I've also contributed a little bit to. And Krylov.jl is an implementation of Krylov solvers that works on all GPU backends. It has been started by Alexis Montoison, and he's actually right now a postdoc at Argonne. So if you want to use Krylov solvers, feel free to send an email. And it has nearly all Krylov methods that exist, and the entire code does not mention GPU once. But it is written in such a way that you can use it on any GPU backend without having any direct dependency of that entire code on any GPU package. It has also preconditioners, Krylov preconditioners.jl that you can use. It works with custom operators, so you can write matrix-free operations, and you could, for instance, then write your operator in kernel abstractions. And here, for instance, I write an example where I use forward diff. So forward diff is able to give you for any function that you write in Julia, the gradient or the Hessian. I use Krylov.jl as a Krylov solver. I use here CUDA now as a backend. And I do using GPU arrays for a reason that I will explain now. I initialize the first point to all -1. So here's the function that I want to minimize. It's easy to see what the minimal point will be. So 1, 2, 3, 4, right? Because then it will be 0. And then I define the gradient, f of x. And I get g of x is then, so I just define a new function which gets mapped to gradient fx. And same for the Hessian. And then I can use CG, conjugate gradient, to do one step, so to solve this optimization problem and get one step back. So I pass in, I mean, this is just, yeah, that's how CG works. I pass in the Hessian, the gradient minus the gradient, and the Krylov method will dispatch and it will return me the minimum point. And now what is nice here is that you could just transfer xk to a CUDA array, and all of this machinery would run without forward diff, Krylov, having any notion of GPUs. They would just, I mean, it's not that it comes free, but they have been written in a way that then allows the GPU abstraction to be applied directly and be mapped to CUDA. But of course, it's not as easy as that. You see here the macro allow scalar, and that comes from the package GPU arrays. If you don't use allow scalar in general in Julia, when you use a GPU package, it will give you a warning if you do scalar, if you use scalar indexing. So if you access a single element of an array, it will tell you, no, don't do that. And then you have to explicitly allow it with allow scalar, meaning that this code is not efficient at all. But it's just to show you, to get it off the ground and get a first code to run that uses a Hessian, a gradient, and Krylov and CUDA is just these few lines of code. And I think this is really the impressive bit about Julia in a nutshell. This is always the example that I show. And why has this so far only been done in Julia? This goes back to that it uses LLVM and does just-in-time compilation. So the code for the gradient here is only being generated at runtime. And this has huge implications also, because if you are using C++ lately, or also for the vendor for getting highly efficient code, they are trying how to optimize that, which usually comes down to that you have to compile for a lot of cases that you run your code if you want to distribute binaries. So for an offline compiled code, you have to compile for every possibility that your program will be called. Everything has to be optimized, and it has to work for every backend that you have, which leads to very long compile times, which is a typical effect that you have when you use C++ templates, for instance. And in this case, it is only, the code is ever only compiled for the combination that you use. So you never have to compile for any other GPU backend. You never have to compile for a different differentiation tool, but you may use later a different differentiation tool, and then it will be compiled exactly using that, or a different Krylov solver, for instance. Although Julia still takes compile time, if it would cache everything, the exact execution path that it does, which with Julia 1.12 it actually does, that's the newest version of Julia, you really get actually very low compile times in total, because you only compile what you execute. Now, there are, of course, also exceptions where this breaks down, and this is mainly when you have really highly specialized vendor-specific libraries. One of those is, for instance, the sparse direct linear solver QDSS by NVIDIA. It's really the state-of-the-art sparse direct solver for GPUs. I mean, we were really hunting a fast sparse direct solver, and this is by far the best that is around. So no other GPU vendor has that. It has a very specific API where you have to initialize it properly such that everything is cached and allocated. And there is a Julia interface, but then it will only work with CUDA. So you don't get for free, of course, that implementation on another architecture. So architecture overview, what in the past has been many core machines and some GPUs has now become mainly only GPUs. So that is what Julia is currently also focused on. And as we see now, Argonne as the next machine will have a NVIDIA GPU, which will position Julia very well, because for CUDA, the support of Julia is really, really great. For Aurora, the oneAPI.jl package is actually currently only maintained by me. It had been initially developed by Intel and what was then Julia Computing, so the company of Julia. But yeah, Intel had cuts, and that was one of the cuts. But oneAPI.jl is still working. You get working code, and I would be interested if you have problems. Yeah, just send an email, and we will work on it. I really try to have support for Intel GPUs, because I also believe even if our next machine is CUDA, for consumers, and if you want to prototype on your local machine, I think Intel GPUs will still be relevant. Yeah. And now Julia at ALCF. So finally we come to the point where you decided to use Julia either now or you had already, and you want to use it on the ALCF machines. So this will focus on Polaris and Aurora, and also go a little bit beyond. So our goal is to have something like modulo Julia, and you just have Julia running. It works with the GPUs that are on that machine. It works with MPI, and it works with the file systems, meaning it can also read certain file formats that are usually used in HPC, like HDF5. And you can make large-scale submissions, not only small ones, but also large ones, and you don't crash the entire system, or yeah, whatever. So it should be smooth. Julia-specific challenges is that it is compiled at runtime, which also means that a compiler will run at runtime on the entire system, which is probably not what you want, because it will compile the same code multiple times on each node, access the file system by every process. And so you have to really think how to deploy Julia. In that sense, it is a bit Python, like Python, because it has to load all these runtime libraries. But also it uses a lot of electricity while compiling that you also want to think about and use most efficiently. So there is a way of offline compilation that also Julia from the very beginning has been working on, but there has never been enough time for it. But it has always been on the to-do list to provide a way in Julia to generate binaries. So you run your code once, and it would essentially cache and create binaries for that execution path and those file types. And the Julia package manager, of course. So most software is managed by the user. And because of this endless combination that you have, like we saw now with forwarddiff and Krylov, and what code will eventually run, it's hard to predict, because it depends really on what package the user is loading. So you do not want to take that out of the user's hand. You want to leave that control to the user, and as little as possible force the user to use certain package versions and certain combinations of packages. And then we have the artifacts system, which is not only for binaries, but also for data files and so on, where Julia codes download the data that they need and the binaries that they need. And you want to keep that advantage and don't make it such that when you rerun a code, it suddenly uses a completely different binary or data. So the current status is still, I would qualify as experimental. We don't have that module yet on the system deployed. I was working on that since August effectively. And there's a documentation for Polaris. I would say it's always good to start with Polaris to do a first large submission and see how it is to work with Julia, because the CUDA support is just there. So you don't run at least into the one API issues. I have created a repository on GitHub, which you see here, on the ANL Sys organization. You check out, there is the module file. You just point it to that module file and you load it, and everything should work. I get a bit more into the details here. So do not install anything Julia related in your home folder, because that is a network file system and you will create trouble. I mean, it will. Julia also has a lot of files. When it caches, it essentially creates object files. It's like a compiler. So it will have a lot of object files that are hashed such that it can, where the names are hashed, you don't even know what it is for. Only Julia knows when it goes through the dependency what that object file is actually used for. And that will corrupt for sure at some point if you use it in your home folder. So go into either Polaris or Aurora folder, and there's a setup script which will set up everything. The one thing that you will have to set up, so if you have never used Julia, there's a thing called Julia Depot Path. That is where Julia essentially handles all its files, caches, compiled files, artifacts, other stuff. So also, yeah. And it will install the Julia binary into that folder. So you have to define that, you have to select that folder with an environment variable on a fast file system like Eagle or so on. And it will install the latest Julia. And Julia has a way of specifying certain package options that should be used, like for MPI. What MPI do I want to use when I type using MPI? Maybe the one API library should be initialized a certain way. Do I want to support GPU aware? Do I want to load a GPU aware MPI? All of that stuff can be defined in a local preference file, local preference TOML. And there is one global one, which is also saved in that Julia Depot path for each Julia version. And I've essentially created that. So you will load that automatically and everything should just work. So the only setting that you have to do is set that Julia Depot path and don't set it to your home folder. And then you do module use. So you point it to the folder with the module file. And you do module load Julia, and that's it. And you write Julia Depot path, you export it. Probably you want to have that in your bash RC. All done. Then you can start with your project, either clone one, create one. You just do the usual. So this is now for those who already know Julia. So you do run Julia with the project, you update all the dependencies, all the packages, it will all work. If you have to be aware that you cannot run the code. So you can update here the packages, but you cannot run the code on the login nodes on the GPUs because the login nodes don't have GPUs. So you will have to run for the first time on the actual compute node. And again, as I said before, Julia compiles at runtime. You do not want to compile using 1,000 nodes. You only need actually one. And how you do that is you submit an interactive job and you run your simulation on one node. And that way, it will be precompiled and cached. So when you then later start it, it will load those cached files and it will start up also much faster and immediately execute. Now, this assumes, of course, that your sequential code follows the same computational path than your parallel code, which is not necessarily the case, of course. So that's one thing to think about. there's no easy way right now around that. I don't. They will probably be at some point in the future something that does their smart caching for large-scale machines, but there's no package available right now. And we did also during ECP extreme large-scale runs, meaning full machine runs, just as a demonstration. And what happened is that, for instance, on Polaris, back then, CUDA.jl would use NVCC as the compiler because only NVCC had the full features of CUDA. If you called the library, I mean the compiler as a library where you just pass the IR and get a PTX object out, it would not support everything. Today it really uses that. But back then, so it would call the CUDA compiler, create an object file on disk, which was where the name was hashed. Now, if you do a full machine run, you had suddenly cache conflicts, clashes. And those are things that you run into them. And on top of that, you then have to, so the solution was to move Julia to the local SSDs. And we somehow want to automate that in the future, but it's still not clear how to do that best. So when to move, what to move to the compute nodes. Yeah, the future. So we will support the Intel GPUs the best we can. Intel doesn't support it itself, but yeah, I have, I will invest. I have a lot of time to invest in it, and I also plan to continue to, in particular also because it is a nice learning experience. So if you learn how one API works, you also learn how the other GPU packages work because it is really similar how they all do things. It's just that it is proprietary and everybody thinks has to do his own stuff. The support for CUDA is just far more mature. That's just something to keep in mind. It supports unified memory. It supports really a lot of the features of CUDA, and it's quite robust there. The post-Aurora system will be NVIDIA-based. For me, that was a good news for Julia, because I think that will really give us a robust path forward. And we will roll out a system-wide module in the coming months that will automate all that process of installing Julia. Thank you very much. That's it.